This is Chapter 12 for Chapter 5 of Calculus 3, and in this lecture I will give some applications of the theorems of vector calculus. And just point out here some typical notation. ds refers to integrals along a path in a one-dimensional path. dA is the integral over an area. It sort of makes intuitive sense. dV is integration over a three-dimensional volume. d sigma is the integration over two-dimensional surfaces, for example the surfaces that would bound the three-dimensional volume. N is always the outward normal, may or may not be the unit normal, but it's the outward normal, and k is a unit vector in the z direction, which would be the binormal for the plane areas and curves. Again, I'm just pointing out that I write f with components mn or mn&p if it's in three dimensions. Other authors will do something else. I avoid capital R because it means so many things. It means region, it also means real numbers. You can go on and on with all the things that R means. So I avoid it and use P for that. Everything I've done and continue to do has been in Cartesian coordinates. All the theorems of vector calculus are also written in cylindrical and spherical coordinates. And most handbooks in physics and in math will give those equations, will list the forms of Green and Stokes' theorem in these other coordinate systems. But for right now, all we're going to do in this class are Cartesian coordinates. So for the first example, we'll look at the divergence form of Green's theorem. Here's a statement of it. The integral of the normal components of f, we're calculating flux, the integral of the normal components of flux over the bounding curve in two dimensions is equal to the integral over the area, the enclosed area of the divergence of f. That would be del dot f, the divergence. And again, we're talking about a two-dimensional field in the case of Green's theorem. So here's the example. We're going to look at this function, f equals x squared in the I direction plus x squared y squared in the j direction. This is just a function we're going to consider. It is a vector function giving a vector field. And we're going to look at the semicircular region. If you were to draw it, of course it would look like this. So you're going to go from 3 to minus 3. Sorry, this isn't very isn't drawn very nicely. And there would be the other. This is out to 3 and x. So it's this semicircular region, okay? And we're talking about the whole region in sight. Now, if you want to use the flux integral, in which you find the normal component of the field by dotting it with the outward normal, so here's your outward normals sticking out of this, the whole region, you would have to integrate around this. This surface area, this drawn in red, would have to be parameterized. And you can see from this that you would actually need two parameterizations. One would have to go from here to here, and the other would have to go from here to here, and you'd have to make sure that you were doing it in the right orientation so that you go all the way around in a counterclockwise direction. In other words, you don't want to go up here going in this direction and then by the way you set up the integral go this direction along the straight edge. That wouldn't work so well. So that's what you'd have to do to use the flux integral. You would have to have two surfaces, two integrations, and you'd have to carry all that out. Instead, we're going to use the divergence integral, which is the other side of Green's theorem. So we have to take the divergence and integrate over the area. So the first thing we need is the divergence of the field, which is, remember, that's going to be a scalar. I keep saying this because I get tired of writing it. Okay, 2x plus 2xy squared. That's the divergence of that field. I'm wondering if that's correct. Just a minute. Okay, this is wrong. And maybe it's moderately instructive for me to go through this, or maybe it's amusing since you probably don't make any errors. Okay, if I had f as stated above, x squared in the I direction plus x squared y squared in the j direction, and I took the divergence of f, that would be the partial with respect to x of the x squared plus the partial with respect to y of the x squared y, right? Which would be 2x plus 2x squared y. That's not what I wrote here. Obviously, I used a different function. No, obviously I made a mistake, but that's okay too. Alright, so we're going to continue with this function, this divergence, which means it must have come from a function that looked like this, possibly. We'll say 2/3 xy cubed in the j direction. Okay, this would give me a divergence of 2x plus 2xy squared. Okay, but we're going to proceed with that. So here's our divergence. Now the integral is going to be the double integral over the divergence, and that's a scalar function, and we're going to take it over the enclosed of the area. And the area that's enclosed, you'll have limits in x from 0 to square root of 9 minus y squared, and in y it went from -3 to 3. That semicircle. That's straightforward, easy to carry out, assuming you know how to take the divergence properly. Well, anyway, and you can just get an answer. So what I'm showing you is how you apply these theorems. You can do the flux integration, in which case you've got to parameterize that entire surface or surfaces, or you take the divergence and integrate over the enclosed area. Now let's look in 3 dimensions. So in 3 dimensions we have Gauss's theorem, which is the 3-dimensional equivalent of Green's divergence theorem. And now we state it, here's our statement of it, and we'll consider that volume right there, although that won't be what we integrate over. Okay, if you want to look at the flux, the net flux out of this volume and use the flux integral, then you would have here an integral over the surface. But the surface of this is actually, if you looked at it like that, there would be 6 bounding surfaces. Right? This one, the one on the top, the one on the bottom. I mean, if you could write one function that would give you all those surfaces, good for you, but I don't think it can be done. So you would have to parameterize each one of them. So you'd have R1, and it would be a function of 2 variables because it's a surface. If it's a surface, you've got a parameterization involving 2 variables, and you would have one here, you'd have one up here, so there would be R2, and you would have to make sure you did this correctly. Okay, so this would involve, on this hand, 6 integrals, and it might be easier than the other, who knows. On this side, you take the divergence of the function and you integrate over the volume. If the limits are easy, such as they're all independent of each other, that is particularly easy. So let's consider a box. The limits in x are 3 to 5, y 2 to 7, and z 0 to 0.5. So this is just a rectangular box. And this would look similar to the drawing on the previous slide. So in order to use the flux integral, you would need 6, you would integrate over 6 surfaces. That's in the homework, and obviously you can figure that out. Instead, we're going to use Gauss's theorem using this divergence integral. So let's consider this field. F equals 2x in the I direction, 3x in the j direction, plus 7z in the k direction. We take its divergence, which ends up to be a scalar, in this case independent of x, y, and z. It ends up just being a number, 12 in this case. Okay, so to compute the flux out of the box, the divergence of f is replaced by its divergence value here, which is 12. Then you just integrate to the limits of the box. They're numbers independent of each other, and that's very easy to take and straightforward. So this is using the divergence integral in of Gauss's theorem to compute the flux out of this box. Okay, now I'll use a different field, and the reason for doing this is because I see occasionally some very simplistic errors in integration, and it doesn't hurt to be reminded. Again, we're going to take the divergence of f. When we take the divergence of f, this is the function I get, cosine x plus cosine y plus secant squared of z. and that's what I'm going to integrate. The limits are the same, it's the same box. But now look, when I integrate in z, what do I get? Some people tend to forget the x and the y here because they don't have a z in them. But when I integrate this, okay, what am I going to get? I still have the 3 to 5 and the 2 to 7. Fine. Now it's going to be z times the cosine of x. Remember, when you integrate with respect to z, these terms are treated as constants. So if it were 2, it would be 2z. In this case, it's cosine x times z. And then you have another z multiplying the sine of y. And then, of course, you get tangent z, and you're integrating from 0 to 0.5. That's why you see the 0.5 here, the 0.5 here, and of course, tangent of 0.5, you get the 0.54 here. Okay, now you integrate in y. Now remember, when you integrate in y, what happens here? You'll still have the limit 3 to 5, but 0.5 cosine x is treated as a constant. So this would be, well, I'll keep the constant in, 0.5 y times the cosine of x, and that y is going to be evaluated. Okay, now you just have 0.5 sine y, fine. The 0.54 is a constant, so you have 0.54 and you have a y there. You must evaluate this between 2 and 7. You still have your x integral left. Okay? And then remember, these two are constants, and as you integrate in x, you will get an x multiplying them, and the cosine, of course, you get from a sine. Okay, so that is another example of Gauss's theorem to compute flux out of a box for a particular vector field. The last example I will do is a curl form of Green's theorem. In this case, we're trying to compute circulation. So we have an enclosed, in 2 dimension, we have an enclosed figure. There's some area, and it's enclosed by, we're calling it ds, but that will have to be parameterized. If we want to use the circulation integral over here, then we have to take the vector field, parameterized accordingly, and dot it with the tangent to the vector. Okay, that was done in previous examples. Here's something that, a notation that you can't really see here because it didn't come out very well. But that little 0 down there, there's a little 0 down there, means it closed. Means it's closed, means this path is closed. So if you have a region like this, the path goes all the way around it and closes on it, and that's what we're looking at. That's why we're looking at circulation here. Okay, now if we're going to use a curl form, we take the vector field, we take the curl of it. Remember, curl is going to be a vector out of the plane, dot it with k. Okay, up here, here's your k, you're going to dot that, and take that, integrate that over the area. This dot product is going to give you a scalar. So we're working with Green's theorem, and so we have 2-dimensional fields. One result that you know immediately, if it is a conservative vector field, okay, a conservative vector field is irrotational. This curl is 0, you're done. So this just, I'm going to just write the result. A conservative vector field is irrotational. The circulation will always be 0. And you can see it right here. Curl of f is going to be 0. Otherwise, you might have to do a lot of work to show the same thing. For this example, let's use this function again. X squared in the I direction plus x squared y squared in the j direction, and we'll see if I can take the curl of that. Okay, we're going to use the same semicircular region before, and now we're going to use the curl integral. So we have to take the curl of f, dot it with k. Remember, curl of f is going to be a vector. Then you dot it with k, so what are you going to get? The k component, all right? And then integrate over the area. So the curl of that is 2xy squared. That would be the x component of it. And you can see that's a pretty easy calculation to do. And you're done. Okay, sorry for moving the slide while it was still going. So then you just evaluate that. It's easy enough. Okay. All right. So those are the examples that I'm giving for the use of the theorems of vector calculus. This is so superficial, it's ridiculous. You can look in the book and you can see many more examples. Unfortunately, this is just the last chapter of the course, and maybe it's not getting the coverage it deserves. But if you spent the first 4 chapters and got a good understanding of that, and you have a good understanding of Green and Gauss's theorem, and the curl theorems and the Stokes theorem, you'll be able to go on, and you shouldn't have any trouble. It's better to have a solid background than to go too fast in things anyway. All right. That's it for the lectures. If you have questions on the homework or the sample exams, just contact me and I'll try to answer your questions. Also, if you see any typos, obviously I have lots of them, please send them to me. I appreciate them. I write all this stuff myself and I don't have anyone proofreading it, so there are errors. There are errors. Anyway, thank you very much for attending this course. I hope you learned something and that it's very beneficial to you in the future.